So I know that your test is going to have 3 parts. I kind of have an idea of what I'm going to do: multiple choice, and then vocabulary, and then short answer. I think the short answer are going to be kind of like sketches. So I think that'd be kind of fun. Maybe label things. I don't know. It's kind of what I have in mind. We'll see. Okay? All right. Well, we're going to talk about stars today. And, we just briefly talked about constellations on just a few slides at the end of the lecture on Friday. So if I do anything with constellations, it's going to have to be with like the Big Dipper, and that kind of comes to mind. But I want to talk a little bit about stars. Some of us have darker skies than others to appreciate the stars more. I live in town in Burlington. It's not too bad, but dark skies are just, oh my gosh. So one of the things about stars is we want to know how far away stars are. And a good unit of distance is the light year. So I brought in Buzz Lightyear to kind of, remind you about that. So light year, actually, some of you may know, is basically how far light will travel in 1 year. And here's where I say kind of like, when we turn on the light bulb in this room, you think, well, I see light right away. Well, sort of. The whole electricity going in the light bulb, exciting the gas in the light. So the electrons then get excited, and they fall back down, and they emit a little bit of light. That comes to us, but actually it takes a little bit of time. So what this says basically, I guess what it's saying is when you turn on a flashlight, okay, and if that flashlight was strong enough, those photons, okay, would travel a certain speed, and that speed is 300, I'm drawing a blank now, but it's really fast, okay, and how far they would travel in 1 year, okay, that actually is the distance, bless you, how far they travel in 1 year is the distance of 1 light year. Okay, so in terms of miles, it's about 5.88 times 10 raised to the 12th miles. So it's very far away, a light year. The nearest star to us, and I don't think I have it in my notes, the nearest star to us is actually the star called Sirius. It's the dog star in Canis Major. And it's about that's the brightest star. The nearest star is about 4 light years from us. Okay, so I mentioned that the whole shining a flashlight and how far it gets in 1 year that photon gets, that's 1 light year away. Well, the moon is about 1.29 light seconds. So it takes about 1.3 seconds for light from the moon to get to us. Okay, the sun is farther from us than the moon. Actually, it takes 8 minutes for us to get photon energy from the sun. It takes 8 minutes for light to get from the sun to the earth. So that's kind of the old adage. If the sun were to turn off now, it would be a delay of 8 minutes before we would get that information. Okay, we'd still be shining for 8 minutes. Okay. To Mars, it takes about 13 light minutes. Okay, it takes about 13 minutes for light to travel. So the distance is 13 light minutes. Nearest star, 4 light years. One of the last things we'll have time to talk about, and we'll talk about tomorrow, is the fact that our star actually is on the Milky Way galaxy. So our star, and I'm going like this because actually our star is moving around the center of our galaxy. Okay, but our galaxy, the Milky Way galaxy, is about 100,000 light years across. Just like, I don't know if you're familiar with the Monty Python song. But anyway, it's right. It's about 100,000 light years side to side. That's how big our galaxy is. So one other unit of measurement, and actually I'm going to be talking about this here in a minute too, and it's a far piece, even farther than a light year, is a parsec. And a parsec almost sounds like a Star Trek term, but a parsec is a distance, and it's about 3 1/4 light years. So 1 parsec is bigger than a light year. 1 parsec is 3 1/4 light years. So this figure might look familiar. Way back in this unit of material, we talked about how our star is born, and I think we called it the condensation theory. Okay, other textbooks I've used call it the nebular theory. But basically, here's a 1 right here. Our sun, our solar system all started in a thing called a nebula. And I talked about what a nebula is. Basically, it's in outer space. It's a cloud. That's what a nebula is. So our sun started in a nebula, and all the stuff that was going to make the planets was also in that nebula. And then we had a stimulation. Basically, it began to contract. You can kind of see something kind of warming up in the middle. That's going to be our sun. You kind of also at number 3 kind of see some little thingies flying around the sun. That's going to be our planets. They continue the snowball effect. That's number 4 here. The difference between 4 and 5, I think I talked about before, is in 5, the sun is turned on. And one of the cool things about the sun is basically it has this solar wind going on. It kind of cleared the newborn solar system of all the kind of the extras. Okay, so that's how our sun was born. And other stars are born similarly. Oftentimes, stars are born in sets. I've heard the term called a stellar nursery. Isn't that adorable? Like if you go to the hospital, you peek in at the nursery, all this little babies born about the same time. Well, a stellar nursery basically means you have something that's bigger than the nebula that formed our solar system. It's a humongous nebula we actually call a molecular cloud. So you can have pockets of stars being born. It's wonderful. Giant molecular cloud, a molecular cloud. So these are not necessarily baby stars, but these are all groups of stars that were born about the same time. Okay, this right here, actually I'll kind of draw on it. This is an open cluster. Open cluster. Okay, if you've ever heard of the 7 sisters, okay, the 7 sisters, it's also called the Pleiades. And actually, right now, this cluster of stars is kind of rising earlier and earlier. It's part of the constellation Taurus the Bull, so that's an open cluster. And over here, this is a globular cluster. I'm not sure which one this is. But globular clusters are one of my favorite sort of thing to look at through the telescope. Globular clusters are a bunch of stars that were born about the same time, and they're like a ball. Okay, they're beautiful. The other thing is sometimes, and actually most stars, I should say, most stars actually have a buddy star. And so what you're looking up here is a pair of stars that are gravitationally associated with each other. They're buddies. They were born about the same time, so that makes sense, and they were kind of close together. So actually, we've talked about how, the moon orbits the sun, and, the moon orbits the Earth, and the Earth orbits the sun. So actually, these two things kind of orbit what we call a common center of mass. Kind of do a little dance here. I believe this is a star called Albireo. This is one of my favorite things to find in the nighttime sky. The star's name is Albireo, the bright one anyway, and it looks like one star. And you look at it on a telescope, and actually it resolves, into 2 stars, a pair of stars. And it is in the constellation Cygnus, the swan. Cygnus, and actually that was one of the ones that we looked at in late Friday. Cygnus is the constellation. So one of the things about stars is that other than being beautiful, a lot of times they look different to us. Okay, and you're like, oh, I think something's going on different with them, and they are. Okay, a lot of times they'll have, for instance, different colors. Okay, this is actually, I think, a famous picture taken by the Hubble Space Telescope. I might have mentioned this, but we actually, if my fist is the Earth, we actually definitely have telescopes that are orbiting the Earth so that they can look out and not have the Earth's atmosphere bothering them, not let alone light pollution, that sort of thing. So we see different colors, okay? We see different intensities. We see bright stars, we see dim stars. And they're telling a story with regard to their color and their brightness. Okay, so you might imagine there's probably something different happening, for instance, in, let's just pick one. There's something different happening in this star, that kind of greenish star, versus kind of this little red star over here. And honestly, I'm going to try to explain this to you, but it could be different because of different reasons. It could be different because they're at a different stage of their life, okay? But right off the bat, I'm going to say it could be different because they started out with different amount of mass. Okay? So if you have a stellar nursery, a giant molecular cloud, that's going to birth a lot of stars, right? It's a humongous nebula. Okay? A bunch of stars are going to be born in this kind of stuff. I think it makes sense that some of the stars will get a lot of matter, and some of the stars will get a little matter to make stars out of them. They'll all be born about similar times, though. So here's the deal: if they get just a little bit of matter, and that there's a certain amount of matter that they need in order to turn on to become a star, but if they're basically low mass stars, then they're going to be reddish in color. Actually, low mass stars are the most common. By far, they are the most common for sure. But the thing is that they are dimmer. They are significantly dimmer. So these kind of low mass stars are relatively dim, so we don't see them. And they live a long time. Like, for instance, there is a low mass star that will live 100 billion, let's see, 100 billion years. Right? So here's the deal. With regard to the age of our universe is looking like it is about 14 billion years old. Okay, that's how old about our universe is. So my point is, if you compare those two numbers, okay, basically you have stars that have begun their life and they just have never died ever since the universe began. So high mass stars then, they don't live as long. Okay? High mass stars don't live as long. So for instance, how's this go? If there was a star that was about 10 times the mass of our sun, it would live about, I think it's 100 million years. 100 million years. Our sun is going to live about 10 billion years with a B. Okay. Oh, wait a minute. But before I go on, you caught this. So I want to compare and contrast. So we said low mass stars live a long time. They tend to be red in color. High mass stars, they are the blue ones. And they are, I'm going to add to this, because I said they're dimmer. I said the less massive stars are dimmer. The more massive stars are, guess what? Brighter. Okay. And those are the ones that catch your attention when you walk out the door. Okay, it says blue, but sometimes they actually kind of look whitish. White, if you see a star that looks white, that's a massive star, hot star. So, how bright is that star? And this falls under the category in science, don't blame me, because I didn't come up with a system on how do you say how bright a star is. But how bright a star is, we use we call it its apparent magnitude. We use a little m. And actually, I'm going to hand these out. This is a sky map for November. And it's got two sides. This side, the dots, are the stars. So actually, if you look down here, at the bottom here, it says star magnitude. That's the magnitude we're talking about. So under the category of don't blame me, I'll go to the next one. Okay. So the deal with how bright a star is, actually, we're going to say, nice cat, not only how bright a star is, but how bright other objects are. The problem is that the higher the number, the dimmer it is. And it's all kind of based upon back in 129 BC. And I like to think of Hipparchus as like stretched out, enjoying the nighttime skies in Greece, I guess. And saying the dimmest star I see is +6, and the brightest star I see is +1. That's what he did. He did +6 dim, +1 bright. So the thing is after that, and we kept that system, after that we found things that were dimmer than +6 and that were brighter than +1. So what are you going to do if it's brighter than +1? Well, you're going to continue on, even going into negative numbers. Okay? So that thing that I gave you, so for instance, if you see like the biggest dot says star magnitude -1. Okay, that biggest dot, and I know it's hard to say what the size of a dot is, but to me, the star called Vega up here, that is a -1 apparent magnitude. So that's kind of how that works. This could be kind of helpful, kind of fun. This actually, the web address where I got it is on the bottom here, skymaps.com. It's a good one. The thing is, as you might imagine, since the Earth is orbiting the sun, we get privy to different stars. So this actually has to come out monthly. So actually they have one monthly. This is as of the middle of the month. So about the middle of November, I think it was about 9 p.m. or so, this is what the sky is going to look like-ish. So that's pretty good. So one other thing before I move on is that one step in this scale actually is a magnitude of 10. So if you go from a magnitude of 0 to a dimmer star of like +1, because you're going up, okay, from 0 is brighter, +1 is dimmer, you're actually going dimmer a factor of 10. So it's a base 10 scale. All right, so here are some objects as they appear, their apparent brightness. Never look at the sun, right? But actually it has an M value of almost -27. Like, dude, really? Yeah. Okay. Full moon, almost -13. Venus, when it's brightest, which is pretty bright night now, -4.4. Okay. Sirius, the dog star, -1.44. Again, Hipparchus, he came up with our naked eye, what's the best we can do under dark skies? And that's a magnitude of +6. So also on here then, binoculars, gather a little bit light, extra help gathering light. You can up that from a +6 to a +10, but you wouldn't be able to see Pluto through binoculars, okay? But you would be able to see Pluto using the Hubble Space Telescope. Okay, so that's kind of how that works. How bright is it? Now, I also want to talk a little bit about another kind of brightness scale. This is how bright it appears, but one of the things we have to take in consideration is the stars are different distances to us. Okay? So if a star is dim, for example, we don't know if it's because it's kind of not pumping out much energy, or is it dim because it's just so far away from us. Okay? So that's kind of what we're faced with, kind of how the brightness of something appears. So we can't do it with our naked eye, but what scientists can do is basically, we call it, it's a type of normalization. Basically put them all on the same playing field so we can compare apples to apples. So what we do instead is to take all of the objects, and we don't really move, because you can't move a star. But the computer and scientists can actually say, well, what if this star was moved and located the same distance from us? And then we look at the brightness. Then we're comparing apples to apples. And that distance they picked actually is 10 parsecs. Okay, so remember PC stands for parsecs. So if each parsec is about 3¼ light years, you're talking about 32 or so, 33 light years away. So what they do is they kind of think of locating everything, the same starting line, and then looking at it one more time. And then see how bright it is. So things kind of change up a little bit. So our sun, which actually is an apparent magnitude, a little m, of -27, because it's really bright, but our sun is bright just because it's close to us. As it turns out, when we compare our sun to other stars, our sun is kind of like right in the middle. It's kind of like not too hot, not too cold. And actually our planet is just the right distance from the sun to support liquid water and solid water and gaseous water. So my point is, if we were to take the sun, and I don't encourage this, and move it, instead of 1 AU from the Earth, move it 32 light years from the Earth, okay, it would look like apparent magnitude of +4.9. Okay, we could see it, naked eye, hopefully, because +6 is kind of our limit under dark skies. But They just look like another star. So that's the what we call the absolute magnitude scale. And here's where I can complain too. Instead of coming up with a different variable, all they did was to take the little m and make it a big M. So a big M is that absolute magnitude. It's kind of so we compare apples to apples, putting all stars or all anything at 10 parsecs from us. So here's the deal. If you do go ahead and remove the effective distance by putting all stars the same distance from us, so we can kind of compare them, then actually, scientifically, we have a good way of kind of saying how much energy are they putting out. Okay, so actually, it's a good way to examine kind of the health of the star. How much energy is it putting out? All right. So let's talk color. So this was one of the things we covered in our physics unit was this idea of different forms, I call them cousins, different forms of energy, different forms of electromagnetic radiation. So you see up there, gamma rays are the most intense energy, okay, and radio waves are the least intense energy. We talked about that. Kind of in between is you see the Roy G. Biv, so going backwards, remember I kind of tease, it's red, orange, yellow, green, blue, indigo somewhere in there, and violet, okay? So this is the lowest energy, and this is the highest energy. So already this morning, okay, we said that the hottest stars are going to appear bluish, and the coolest stars are going to appear reddish. And actually, that's consistent with what we've talked about. Sometimes students, and I understand because we grow up and you're like, ooh, red hot, like red hot. But no, actually red is the coolest color of energy-wise. So I think we talked about Wien and Stefan Boltzmann's law when we talked about energies. And so we actually have, these are the radiation curves I think we talked about before. Okay, here's a curve for a star that is 15,000 Kelvin. Okay, you guys actually had a homework question, how hot is the surface of our sun? And it's about 6,000 Kelvin, more specifically 5,800 Kelvin. This is actually kind of the fingerprint of our star. Here's the fingerprint of a cooler star. And then down here, a human being, if you were to kind of say what sort of radiation are you emitting, this would be kind of what your little curve looks like. This is our little radiation curve. Is that not adorable? What does that mean? It's clear down there. Well, it's clear over here in long waves, okay? Actually infrared radiation. And the other thing, it's pretty short. Its intensity is pretty low. So we are not as hot as a star. Glad to hear it, okay? So this right away then actually kind of gives you a sense for why stars that are hot are blue and why stars that are cool are red. Okay, they're peaking at blue if they're hot and they're peaking at red if they're cool. The other thing we said is I told you to put dimmer for the low mass red stars. Okay, it's dimmer, and brighter for the high mass blue stars. So it's all good. So remember when we talked, I think it was it chemistry or physics? I get them mixed up. But when we talked about an atom, we said actually we have a center of an atom called the nucleus. And protons and neutrons are tucked safe in the nucleus. And then we have electrons outside, okay? And we said actually electrons can be excited, okay? And if they're excited, actually they can create, and that's what I have up here. If they're excited on the way up, they can nab a little bit of energy. So actually these are examples, the O, B, A, F, G, K, M. These are all examples for basically they're individual ones, so we can pick on O. This one, okay, those lines, those dark lines, are where the electrons have robbed energy to become excited. Darker line spectra. Okay? We could have an analogous bright line spectra if we watch the electron fall back down to the ground state, but these are dark line spectra. Now, the deal is that these are actually not just any spectra. These actually are spectra that came from stars. So these are like fingerprints. Do they look kind of like DNA? I don't know. I'm not a biologist, but they run it and they kind of get these lines, and then they go to a library or they match up with somebody else. The lines matches up with somebody else and they know the identity. But these, if you know what you're looking for, basically differentiate stars into these 7 spectral types. So the 7 spectral types are over here. What I'm circling are the spectral types from hottest, and actually you can see how hot it is. So for instance, that's a 30, the surface of that star is 30,000 Kelvin to the coolest. Cool. The surface of that star giving that fingerprint is 3,000 Kelvin. So over there under spectral type, that actually is what we say classify that star as. So you guys told me, or we all agreed, that hot stars are blue. And so actually our blue stars are going to be our O-type stars. Our red stars are going to be what we call our M-type stars. Okay. As they are at a certain stage of their life, anyway. So the OBAFGKM, from hottest to coolest, one way to remember it, a mnemonic device, is this little phrase, oh, be a fine guy, kiss me, guy or girl, kiss me. So each letter stands for. Yeah. Okay. So scientists love their data. And one of the things, let's see, what year was this? Maybe early 1900s, I want to say. One thing that was coming in was a lot of information about stars with regard to their, how hot they are and how luminous they are. And that's to say how their absolute magnitude, how much energy they're putting out. So how hot they are and how much energy they're putting out. So what these folks did in 2 different continents was to basically make a scatter plot. So what a scatter plot is basically you pick the things that you think that are going to be related. In this case, with regard to a star, what they thought was going to be related was temperature and, like this said, absolute magnitude. Okay, so how bright it's a real brightness, absolute brightness. Okay. So what they did with their scatter plot, and you're going to see it here in a minute, was basically they saw some trends in the data. They saw that if you go to the cooler temperatures, okay, you ended up with a set of stars that had kind of low brightnesses. And if you go to your hotter stars, ended up with a set of stars that had high brightnesses. Okay, so they were real excited about that line. The other thing, though, and I'll show you what this plot's going to look like, they also came up with a cluster of stars up here and a cluster of stars down here, and they explained all of that. So that's called an HR diagram, Hertzsprung-Russell diagram. So here's an HR diagram. Again, what's along the x-axis is temperature. What's along the y-axis is, and I think we defined luminosity when we were talking about our sun. Luminosity, or energy that a star is pumping out. Each one of these circles is a star. I like this HR diagram because it even gives the names of the stars. So you see the diagonal that I was talking about right here. Okay. They're real excited. Oops. And then you kind of see the 2 clusters of stars. Here's like a cluster of stars up here and a cluster of stars down here. So here's the deal. This sort of kind of scatter plot, and based upon other things they know, scientists could start to put together the pieces. What this diagram does is basically tell us how a star lives its life. Okay. This number 1 right here, well, this is not number 1. I'll put a 1 here. How's that? 1, that's the diagonal. It's called main sequence. That's a stage of a life of a star. This up here, I'll put number 2. I'll put actually 2 and 3. Okay, 2 and 3 are together. It's a stage of a star's life. Giant and supergiants. White dwarfs, I'll put down here. It's a stage of a star's life. And I want to kind of talk about the different stages of a star's life here. Okay, but that's what the scatter plot did for Hertzsprung and Russell, and for us. So the main sequence, that diagonal, that kind of where they all saw that they kind of landed on an X, kind of going from the upper left to the lower right on an HR diagram. That right off the bat, well, a few things. I'm going to go ahead and add this main sequence. I'm just going to say it is totally the longest stage. It is long, long, long. All stars live their longest part of their segment on main sequence. The other thing is that actually main sequence, you can see that these are massive blue stars, and down here we have low mass red stars on the main sequence. The giants and supergiants and the white dwarfs, they don't really play along as much as the main sequence stars. So main sequence, what's with the main sequence? Maybe this will kind of ring some bells when we said, how does our sun produce energy? Well, we said basically it's doing this. Our sun is taking hydrogen and fusing it together to make helium. So what a cute little figure I got off there. Okay. So what our sun is doing is main sequence stage. Our sun is in the main sequence stage. And I think I told you that we're about halfway through this before we blowed out. So about 5 billion years is how long we've been doing this, our sun, and it's got about 5 billion years more, for a total of 10B with a billion years. Okay, so the first stage of any star is the main sequence. Okay, and so this actually is something I already said this morning, that the massive stars live their lives more quickly. And if you look a little bit closer into it, basically what they're doing in their cores is basically like nuclear fusion on steroids. Okay, since they're so massive, they kind of have an extra mechanism to go so fast. So they burn through their hydrogen a lot faster. So how do they live their lives? Let's see. For massive stars, they only can burn nuclear, this sort of fusion for 20 million years. Okay, we're about 10 billion years for main sequence. Low mass stars, like I think I said before, 100 billion years. So what can we expect from our sun? Like I said, our sun has about another 5 billion years worth of hydrogen to go ahead and keep doing this. But once it kind of peters out of hydrogen, because it's going to be converted to helium, then it's going to swell out. When it swells out, it's going to become, remember on the HR diagram I said giants and supergiants, it's going to move up there on the HR diagram, literally. So it is inevitable. I mean, you can't like ignore that you're going to run out of hydrogen. So stars will run out of hydrogen because it's switched from hydrogen to helium. So what are they going to do when they just have helium? Well, it depends on how much mass they have. Okay. What happens next depends upon how massive it was. For low mass stars, for really low mass stars, low mass stars, basically when they're done with the hydrogen in their core, they don't have anything else to do. So they just kind of cool off and they're done. The cool thing about stars, though, is the universe believes in recycling. So a lot of times, some of that star stuff can be go into making new stars. Well, if you go ahead and up the mass, okay, it's not a low mass star, but it's still kind of low mass. So if you go somewhere between 40% or 0.4 of the mass of our sun, up to 8 times the mass of our sun, the outcome is different. It can go a little bit longer instead of just becoming a brick. Okay. What they will do actually, we talked about elements, and of course an important element is carbon. What they will do is actually fuse helium to form carbon, because they're a little bit bigger. But that's it for them. Okay. Once they form carbon, they're going to end as a white dwarf. So did you remember on an HR diagram, the white dwarfs are, if this is my main sequence, white dwarfs are right there. Okay, so that's actually what they're going to end up as. Well, what if they have more mass than 8 times the mass of our sun? Well, the cool thing is if they're between 8 and 25, what we say solar masses, or 8 or 25 times the mass of our sun, they're going to blow up. Okay, so they're going to go out a supernova. You've probably heard of that term before. Supernova is an explosion. Actually, there's a couple types of supernova, but this one is where a massive star ends its life. It blows up. It will blow up. Now, massive stars that end their lives, after they blow up, okay, they leave kind of this, and we have a picture coming up, what's called a supernova remnant, kind of that's their guts. But the little core of what used to be the massive star stays intact. Now, that can either be a neutron star or it can be a black hole. So basically, the last scenario for a high mass star is one that is more massive than 25 times the mass of our sun. It's going to go supernova. It's going to give you this guts called a supernova remnant, and it's going to leave something behind. It's called a black hole. Okay, so that's the difference. It's either a neutron star or a black hole. All right. So let's look at kind of those low mass stars. Not the low mass stars, but the ones that end up as white dwarfs. This is actually what our sun's going to do. So here's your HR diagram. I don't know if you recognize it. Along the x-axis we have temperature, and along the y-axis we have luminosity, or absolute magnitude, the real brightness of the star. And so it is going to, right now our sun is main sequence. So we kind of pick up right here. This is our sun right now. And in 5 billion years, it's going to move up and become a giant. Okay. And then actually the star, and I didn't talk much about it, but the word variable, it kind of is going to pulsate a little bit. Okay. After it's a giant, it's going to make carbon in its core. When it's done with that, actually, it's going to kind of eject its material. And I have some pictures here to show you of something called a nebula, specifically a planetary nebula. The problem with the term planetary nebula is it has nothing to do with planets. Okay, basically, there's a central star that is retired, and it's just kind of gravity. It's lost hold of the stuff it worked so hard to make. It's like, well, my in-laws passed away kind of in the last couple years, and it's like they had a nest egg, which they, their kids inherited, but their nest egg is just gonna, what I'm saying, kind of sad. I'm gonna spend all my money before I die. But anyway, that's the planetary nebula, okay, and then it's gonna cool off to become a white dwarf. So it, the main sequence, giant, white dwarf. That's kind of what it's going to do. So here's a picture of one planetary nebula. And planet or nebula, a lot of times stuff in cool things that you look at in the nighttime sky with a telescope, they have these proper names. So there's only one Eskimo nebula, and it happens to be a planetary nebula. Do you know what I'm saying? So that's kind of how that works. Then the high mass stars, okay, more than 8 solar masses, and I don't think I differentiated between the forming a neutron star or black hole. Here's a figure to kind of show you from left to right how that works. Okay. So again, if we just kind of pick it up here with it being a high mass star on the main sequence, this would be a main sequence. what's it going to do next? It's going to move in the upper part, okay, super red giant, and eventually it's going to blow up in a supernova. Then over here, what's going to be left behind is either a black hole or, excuse me, either a neutron star or a black hole, depending upon its mass. So this right here actually is the guts of a supermassive star or a high mass star. This is a supernova remnant, okay? I believe that is Messier Object 1, M1. And I think it's called the Crab Nebula. So I brought this. Oh, we have to talk about it.
This picture is on this one and this one.
Oh, good. Thank you. Perfect. We're doing good. I'll go ahead and say M1. Now, here's the deal. The thing I gave you, if you look at the back, okay, it actually says things that you can see with your naked eye, things that you can see with binoculars, and things that you need a telescope for. So I just really like this. Notice you see a lot of M things, okay, M. When astronomers or just kind of casual observers find something cool in the sky, you know, we want to be able to kind of say what that object is. And actually Messier, back in the 1700s, was looking for comets, okay? He was looking for comets. Now, we talked about comets. Basically, comets will kind of change their position as they go to orbit the sun against the background stars and go away. So these things were pesky to him. So he's like, he hired some grad students to basically say, take these things and catalog the darn things so I don't say they're comets anymore. These are things that actually, a lot of things you can see with your naked eye. I don't know if you kind of tell some open clusters. Okay, you probably can see some globular clusters up here. Okay, different Messier objects. So that's actually the M things. So M1 is right here, okay, little box with M1. And they're different types of objects, but that's kind of the thing behind the Messier objects. All right. So some other planetary nebula, again, they have nothing to do with planets. I think they got called that because they kind of looked like planets, okay? This is the Helix Nebula. I think that's sometimes called the God's Eye Nebula. The Gum Nebula, I don't know, looks like a piece of chewing gum. Okay. So in there is a retired star. That's just material that's kind of ejected from the star. The Butterfly Nebula, okay, and Glowing Pool Nebula. So they kind of take on different colors and different things. So I'm just debating. All right. So a massive star, something that's more massive than 8 times the mass of our sun, leaves the main sequence, becomes a red giant, okay, then will blow up, okay, and what's left behind, the corpse of the star will either be a neutron star or a black hole. So I want to kind of talk about a neutron star and a black hole. So a neutron star, you might pick up. Well, I know what let's see, proton, neutron. I know what a neutron is, right? Neutron in the center of an atom, right? So here's the deal. What happens basically is there's so much gravity near the end of the life of that star. There at the end, when it goes supernova, the protons and the electrons for the atom squish together and they form neutrons. Like, is that crazy or what? So this object is not normal matter. It's basically neutron soup. It's very, very dense. So if you were to successfully take a teaspoonful and bring it back to Earth, it would weigh 1,200 tons. So it's very dense, very dense object. Now, you might say, well, how do we know that this object exists after a star explodes? Well, one of the things is for neutron stars, they leave behind what's called a pulsar. So the term here, you probably had to turn it in. It's a pulsar. Where did it go.
I think it's on the bottom.
Oh, thank you. One more. Okay, thanks. Thanks, Heather. That is the signature. A pulsar is the signature for presence of a neutron star. So basically what happens with the pulsar is if you guys are the Earth, okay, and the pulsar is spinning, it can actually have a band of energy that comes out kind of like this. And so if you guys are the Earth, it goes, so you see it. It's coming from a pulsar. So the pulsar is spinning, but its axis of rotation is kind of off from this kind of beam of energy that's coming out. Okay, so pulsars are the presence signature of a neutron star. One last thing, black holes, something light to leave you with. Okay. One of the things I think I want to emphasize on here is how do we know black holes exist? Okay. You're like, dude, one of the things about black holes, if you've kind of dabbled in reading about what a black hole is it's black because basically no light can leave it. It cannot shine any light because no light can leave a black hole. Black holes, there's different ways to get a black hole, but remember I said how dense a neutron star is? Black holes are even denser. Matter is basically packed beyond what we say neutrons able to keep it up, so matter just kind of collapses in on of itself. And the way I look at it is it creates a hole in basically space. And space and time are kind of one thing according to Einstein. So there's your hole, black hole. Now how do we know black holes exist? Actually over here, this HDE 226868, that's a live star. That's a real star. Basically, can you see some of the stuff siphoning off of the star, kind of falling into the black hole? That stuff gets really hot, and it creates a signature of just crazy hot energy. And that's what we see is the presence of a black hole. Okay, stellar black hole anyway. All right, so here we go. These will be due on Wednesday. And like I said, on Wednesday, what I'm wanting to do is just talk about galaxies. We won't talk about the universe, the structure of the universe right now, and just kind of hit galaxies and then have a review session and then call it a day on Wednesday. So page 543, short answer, number 14, 17, 20, 22, and 29. Bingo. Thank you, ma'am.
And not this week, but the week after. I don't know if I told you, I will be gone.
Yeah, like which days?
Wednesday, Thursday, Friday. It's the 11th.
Okay.
13th.
Thank you.